presenting my work on PEN 2021. So the title of my work is Wideband View of High Frequency QPOs of GRS 1915 plus 105 in software variability classes observed with AstroSat. So first of all, we have to know what is a quasi-periodic oscillation. So from observation, what we have is that the count rate variation of count rate in time series. Now if any information is present in this particular time series, then it is impossible to extract from this random nature. So one have to go to the Fourier domain of this particular time series. So if we do this Fourier analysis, we could see that this kind of feature quite often appears in the power density spectra. So these narrow peaks are called the quasi-periodic oscillations. Now it can be modeled with a Lorentzian profile, and basically it characterized by the quality factor of the peak, that is the centroid frequency divided by its FWHM, the fractional RMS amplitude, that is the power content within the QPO, as well as that implies the fractional variability that is associated with this QPO in the time series, and the significance of this peak, that is how much significant the peak is with respect to the error in the PDS. So that is defined as the norm divided by its error. So depending on the frequency range, it can be classified into two classes: the low frequency QPO, which lies in the range of frequencies which is less than 30 Hz, and for high frequency QPO the range is 30 Hz to 450 Hz. Now it is well known that low frequency QPOs are actually connected to several spectral states of black hole binary systems. Now what about high frequency QPO? So from the range of frequencies in case of high frequency QPO, we see that this is actually matches with the Keplerian frequency of matter orbiting at innermost stable circular orbit of the black hole. So it is obvious that it originates from the region very close to the black hole and carries the effect of the strong gravity near the black hole. So with being motivated with this motivation, so we currently looked into several observations of AstroSat from 2016 to 2019 time span of this source GRS 1915 plus 105. So from the variability pattern in the light curve as well as the distribution of points in the color diagram, we could identify total 7 classes in our analysis. So that is theta class, delta class, rho class, kappa class, omega class, gamma class and chi class. And we did a static power density spectra in 0.01 to 500 Hz range for all of these classes, and we identify that for a delta class, kappa class, omega class and gamma class, the frequency at the high frequency QPO is present near 70 Hz. So in our entire analysis, we could identify the high frequency QPO features of frequency 68.14 Hz to 72.32 Hz. Now to understand the energy dependent behavior of these high frequency QPOs, we segregated the whole energy band of 3 to 60 kV into 3 major segment. So the first one is 3 to 6 kV, the middle one is 6 to 25 kV and the final one is 25 to 60 kV. And for all the classes in which we could see the high frequency QPO feature, we see that the QPO is present only between 6 to 25 kV energy band, and other two energy band is actually featureless. Also in omega class and gamma class observation, we could see a sufficient duration of high counts in the light curve as well as small count dips in the in between two high count duration. So we intend to study that which part of the light curve is actually generating this oscillation. So for that purpose, what we did, we segregated the whole exposure time into 32 second of segments and did the power density spectral analysis, and we see that the power near 70 Hz is maximum according to this color bar when the light curve contains high count duration, and during the dips the power is less. So we conjecture that the high frequency QPO only appears during the high count region of the light curve only. And for gamma class also the same trend follows. For gamma class we have only high count duration persistently. So as expected, the QPO is also present persistently during the entire exposure time. However, in between 500 to 750 second, the feature is diluted somehow. That is because of this low count dips of few duration that may dilute the feature little bit. So the bottom line is the high frequency QPO appears during the high count rate of the light curve. So to connect this spectral these timing properties with the spectral properties of the source, that means the accretion dynamics, we have did the spectral analysis in 0.7 to 50 kV energy band. So we have obtained the broadband spectra from taking data from SXT and LAX-PC of AstroSat, and we model with the physically motivated model in THCOM as well as power law. So this NTHCOM component takes care of the emission that is responsible for the high that is responsible for the comptonization component. That is, the soft photons from the disk will get inverse comptonized in the high energy electron present in the coronal structure, and that will produce the high energy tail of the spectrum. Also, we see that the comptonization component dominates up to 25 kV energy band only, and after which power law mainly dominates the spectrum. And from timing analysis also we see that the RMS is increasing in 6 to 25 kV energy band, and the associated flux of the NTHCOM is also increases and becomes prominent in this energy band only, beyond which the flux is almost negligible. Also, so these are two results. Now we have few observations for which we have the QPO feature and for which we don't have the QPO feature. So we have compared the spectral properties of these two kind, and we find that whenever the QPO is present, the comptonization contribution is more. That means the norm of the NTHCOM is more, as well as the flux of NTHCOM is also lies in the higher side. So which generally indicates that whenever the QPO is present, the comptonization component dominates in the 6 to 25 kV energy band. So with these results, we conjecture that the high frequency QPO that we observe in the GRS 1915 plus 105 source, that could be a result of the oscillation of the comptonizing corona near the source. So now I will conclude the results. So several analyses have been done on high frequency QPOs from RXT and AstroSat observations, and in this work we only find the QPOs in these four classes, which remains softer than the other classes that we included in our analysis. So that may be the possible reason that we only could identify the QPOs in these four classes only. Also, we identify that there exists a particular energy range, that is 6 to 25 kV energy range, in which the QPO is more prominent and the RMS is more, that is the strength of the QPO is more, and beyond which the QPO is absent. So also we conjecture the possible mechanism that can produce this high frequency QPO phenomena. So that is the comptonizing the oscillation of the comptonizing medium. So in a nutshell, in this work, not only we detect the high frequency QPO phenomena in this GRS source, also we try to address the possible mechanism from which it could be generated. So finally, I thank PAIN 2021 team for giving me this opportunity to present my work in this conference. Thank you.